Hello, I'm Hallam Greene from the CCDC, and in this video we're going to learn about screw axes in crystal structures. Many of the symmetry elements for crystal are the same as those of discrete molecules. Both can have mirror planes, rotation axes, inversion centers, and improper rotation axes. However, a periodic three-dimensional structure also has another class of symmetry operations that involve a translational element. These include screw axes and glide planes. In this video, we will look at screw axes. So, what is a screw axis? A screw axis is a symmetry element in a crystal structure. The symmetry operation involves a rotation around the axis, followed by a translation parallel to that axis. You can think of this combination of rotation and translation as drawing out a helix, like the thread of a screw. Consider the simplest example. Here, the hand shape is rotated 180 degrees around the axis, then translated in the direction of the axis each time. In this case, the translation is by 1/2 of a unit cell. Let's consider this same type of axis in the context of a molecule in a crystal structure. Here, once again, the molecule is rotated around the screw axis, then translated parallel to the screw axis to give the position of the next molecule. This repeats continuously along the axis. Here, each rotation is 180 degrees, and each translation is by 1/2 of a unit cell. This is referred to as a 2-1 axis. The bright green lines show the location of the 2-1 axes in the structure. So what does this symbol mean? The larger number, n, in this case the 2, refers to it being a rotation of 360 degrees over n, in this instance 180 degrees. The smaller number, let's call it m, refers to the distance the molecule is translated. Following a rotation, a translation of m over n unit cells occurs in a direction parallel to the rotation axis. In this example, this is a translation of 1/2, or half a unit cell. This will become clearer when considering some examples. Another convention is that the rotation is always anti-clockwise when viewed down the screw axis. Our next example is of a structure with a 3-1 screw axis. The yellow lines show the location of the 3-1 screw axes in the structure. Here, the molecule is rotated anti-clockwise around the screw axis through 360 degrees over 3, equaling 120 degrees, then translated by 1/3 of a unit cell each time. If viewed down the screw axis, the rotation can be seen more clearly. The next structure has a 4-1 screw axis, shown in red. Here the molecule is rotated 360 degrees over 4, or 90 degrees anti-clockwise, around the screw axis, then translated by 1/4 of a unit cell each time. This creates a right-handed screw. Once again, we can look down the axis to visualize the rotation more clearly. We can also look at a structure with a 4-3 screw axis. Here we can view the molecule as being rotated 90 degrees anti-clockwise around the screw axis, then translated 3/4 of a unit cell each time. You may notice that the same pattern is produced by rotating 90 degrees clockwise around the screw axis, then translating by 1/4 of a unit cell each time. This creates a left-handed screw. A final point to consider is that if you take the mirror image of a structure with a 4-1 screw axis, shown here on the left, you create a structure with a 4-3 axis. The two are described as enantiomorphs of each other. As we rotate the structures, observe how the screw axes have different handedness. The 4-1 has a right-handed screw, the 4-3 a left-handed screw. In this instance, the two molecules from the two crystals are also enantiomers of each other. You can think of two enantiomorphic screw axes like two screws with the threads rotating in the opposite directions. Now let's look at a structure with a 4-2 axis. Here the molecule is rotated 360 degrees over 4, or 90 degrees, anti-clockwise around the screw axis, then translated by 2/4 or half of a unit cell each time. As the periodic pattern must repeat with each unit cell, a 4-2 screw axis is coincident on a twofold rotation axis. This ensures that the crystal structure repeats periodically with each unit cell. This next animation shows part of the unit cell of a structure containing a 6-1 screw axis, with the axes, shown in blue, running parallel to the C-axis along the boundaries of the unit cell. In a 6-1 axis, the molecule is rotated 360 degrees over 6, or 60 degrees, anti-clockwise, around the screw axis, and translated by 1/6 of a unit cell each time. It is important to remember that any symmetry element in a periodic three-dimensional structure corresponds not only to atoms or molecules contained within individual unit cells, but to the whole structure. For example, the 2-1 screw axis shown in the center of the unit cell relates not only these two oxygen atoms to each other, or these two molecules within the same unit cell to each other, but also these two from neighboring unit cells. The symmetry element applies to the whole infinite periodic lattice. As we have just seen, a screw axis relates the positions of individual atoms to each other in a crystal lattice. As with all the examples we have seen so far, it may relate discrete molecules to each other, such as in this example of a 4-1 axis seen earlier. In polymeric structures, a screw axis may relate one discrete polymeric substructure to others, such as in this example containing a 4-1 axis. A screw axis can even relate parts of the same continuous polymeric structure to each other. This can be seen more clearly by highlighting the positions of symmetry-equivalent atoms, such as these copper atoms. This structure contains a 4-1 axis. A structure is not limited to having one screw axis. Some contain many. This structure in the P212121 space group has two 1 screw axes parallel to the A, B, and C axes. See if you can visualize where they are. Screw axes can appear alongside a range of other symmetry elements as well, such as glide planes, mirror planes, and rotation axes. We are now coming to the end of this video. We have seen examples of 2-1, 3-1, 4-1, 4-3, 4-2, and 6-1 axes in a number of different structures. There are a few other types of screw axis, and you should be able to work out how these work by applying the rules and principles covered in this video. Try looking at some examples for yourself using the ref code suggested above. You can use Mercury to help you visualize all the symmetry elements and operations. Check out the resources linked below and at the end of the video. Before we finish, here is an example of a screw axis in a crystal structure. Can you recognize what type of axis it is? Watch the animation, and here's a hint. It's one of the screw axes we saw today. That was an example of a 4-1 axis. Did you get it right? Let us know in the comments. If you said 4-3, you were close, but look back and check the handedness of the screw. Thank you for watching. If you enjoyed this video and found it useful, please check out the CCDC channel and subscribe.